Good afternoon, everyone. It's really nice to be joining you here. I know it's a hot day outside. Hopefully after this talk, I can convince you that our GPUs run even hotter. So I'm Paras. I'm one of the co-founders and the CEO of Genmo. And we are pioneers in video generation, and we are a diffusion model lab. Today, I'm going to share a bit about our journey from academia to founding Genmo, and talk about some of the innovative systems that we've built to handle enormous scale and growth over the past year and a half. And so before diving in, I want to just talk about our high-level mission. For us, the driving force to work on Genmo is the question, what if? What if the cost to turn your stories into ideas and cinematic content were zero? It would enable a world where you could go on and turn on a faucet and video comes out. And it's all beautiful, cinematic, incredible storytelling. Good stories can come from anywhere. And so what happens when anyone can make an award-winning film with a push of a button on their phone? And at Genmo, we're working to make this a reality by building the world's best text-to-video engine. And the way we're doing that is by pre-training a large video model for video generation. And I think that large language models, you've heard a ton about it today at the Ray Summit, they represent very much the left brain of artificial general intelligence. That's reasoning, logic, information processing. LLMs are the canonical architecture in this camp with amazing advances in domains like coding, and ChatGPT. But the right brain remains extremely underdeveloped today. I believe creativity and imagination are still severely lacking in the modern LLM paradigm. And at Genmo, we believe that unlocking this right brain is the next frontier in AI development by building video generation models that can simulate anything, real or impossible. We are giving AI the ability to create, visualize, and explore synthetic realities. And we believe these models serve as world simulators, expanding AI's potential beyond problem solving into creative exploration. The canonical architecture on this side of the camp is diffusion models, which have roots back in 2015. I'm very privileged to be able to work with two of the co-authors on the DDPM paper, which is one of the foundational architectures for diffusion at Genmo. And I also believe video is the ultimate creative modality, as it is the ultimate form of communication. Even here, so much of what I'm saying to you is from my expressions and from my body language, not in what I'm saying. And so it combines audio, text, images, and 3D worlds together in a really deep way. So at Genmo, we are a fundamental research lab dedicated to visual intelligence. Our flagship product is Replay, which is an advanced foundation model for video generation. And so given a text prompt or an image prompt, Replay will generate fluid, cinematic, high-fidelity videos. And in this video, you can see there's really interesting water effects. Reflection of light on the water surface is also realistically replicated. And so it's a very powerful base technology for creative exploration. I'm here to talk to you about how we've scaled the product over the last year and a half of our company's life. We now have more than 1.5 million users on our product at scale in 40+ countries. You can actually use it today by going to genmo.ai while you're watching this. But just to give you a quick overview of the end-to-end experience, you can pop in any prompt, and very quickly under the hood, we're provisioning a big fleet of serverless GPUs in 20+ data centers across the world. And so we'll see these workloads begin to schedule as they get placed into different cloud providers. And videos begin to generate. So within 10 seconds, we have pixels streaming off of the GPUs to your browser. And we're really proud to have the lowest time to first pixel in the entire industry. Some of these videos have hallucinations, like this dog swimming has fins. So I do actually think it's nice when you can have hallucinations as a feature, not a bug. But I'll go ahead and give this a few more seconds to complete. And you'll see that the streaming is actually really powerful. So I'll talk about this in the talk, but this enables us to achieve both latency, low latency of generation, and high throughput. So the first generation should be completing shortly. And there we have a fluid video again, a very seamless video here of a dog swimming. And I'll go through some of the other generations here. And again, some of them have hallucinations, some of them don't. The technology is very early. I believe we're less than 1% of the way there to our generative video future. But the tech is real, and you can use it at scale, and many, many people do. So I'm really excited now to talk about how we scaled from 0 to more than 1 million users over the last year and a half. This forced us across many orders of magnitude as we scaled. Every day, our users create several multiples of the entire Netflix video catalog every day in the product. So I'm really excited to discuss our story as we scale this technology from the roots of really scrappy innovation at UC Berkeley in academia to now. I'll also discuss some of the technical pillars that our team has built along the way to endure this rapid growth. So we actually started the company just about in December 25th, so this should have been 2022. That was Christmas 2022. And that's when we started training our first text-to-video model. At the time, we actually were in an AI hacker house that I helped set up here in Temescal, Oakland. So we were in a hyper-creative space, and I think it's wonderful that we could have this kind of energy there. But that was our founding headquarters. And so we started working on training the model there. And in less than a month, we had our first product out to market. So on January 20th, we launched the world's first public text-to-video product to market. I think this is really important because at this point of time, many companies had demoed proofs of concept or had shown papers that had done some form of video generation. But at the time, no product was truly public and usable. And we felt it was really important as academics who were working on this technology to ship this. And so at this time, I started this, and it was just me and my co-founder, Jain. After shipping this, it started to grow pretty virally. But at that point in time, our serving stack was pretty basic. At launch day, we ended up hitting, I think, 1,000 users. And our serving stack at that point was something about just having a simple autoscaler that provisioned and scaled pools of GPUs. It's pretty common workflow for how people do ML serving today. This was actually a really good solution in the early days, but the challenge was how it endured scale. So it's funny, I remember my graduation day, so this is like May 2023. Here actually is my advisor, Jan, who I'm sure you saw earlier with the JNI. And as Jan was hooding me as I was walking off the stage, it was really incredible to see massive user and community engagement, which was vibrant. And so we had just had a new launch that went viral, and from there, users were creating videos, sharing them, and people would ask questions when they would post them to social media, where did you make that? And so we were seeing tremendous growth. At one point, I think as I was graduating, we were acquiring 80,000 users a day for like a short period of time. Obviously, it was not sustained, but to absorb that kind of load with massive scale GPU infrastructure in the back end was extremely challenging. And so since then, growth has continued significantly. And today, we're cleared past more than 1.5 million users, and we have users in more than 40 countries. And this global excitement is, I think, really interesting because video is a universal medium. It's not just about having language models that can speak in English or any particular language. Video is something that can be consumed broadly. And so we saw really fast growth globally. And that introduced really unique challenges from a serving perspective that were particularly unique. At this point in time, we are operating with order 1,000 GPUs across our entire fleet, and so it's very large scale as well. At that footprint, I think our latest data centers place somewhere in the top 50 or the top 500. And we are able to accomplish this serving while remaining 11 times cheaper than alternatives in the market with managed inferencing systems. So this was really critical for us to achieve scaling while managing burn, because video generation is incredibly resource intensive. And so I talked about that first level or stack, which was a pretty bog standard serving stack. And at 100 people, one of the big problems that we hit really quickly were control plane fires. This was particularly challenging. And this would manifest where the product would be scaling, the data plane would continue serving requests, but the control plane could not do orchestration and provisioning and would not be able to serve requests fast enough. And so we would see significant drops in goodput. And so this is unfortunate. This was actually especially bad because we're paying for GPUs behind the scenes. So control plane issues were quite costly, right? Because these were typically CPU VMs. And so it was a shame that this was bottlenecking the GPU infrastructure. And one of the particular challenges we had to deal with here that I think is really interesting and unique is with video generation, with global demand, there's rapid bursts and spikes in capacity with diurnal or triurnal loads. And so as we see a product, here I have a screenshot from one of our monitoring dashboards. This shows capacity in the fleet, and you can see that there are 2 to 3x peak to trough auto-scaling events. And so from the top to the bottom, I mean, the entire cluster is cycling its footprint extremely quickly. And that's tied to user demand. One of the other challenges is we're big believers in large model training. And so we do train large video foundation models. And so that means the parameters can be very large. We're quite experienced now serving Docker containers with orders tens to 100 plus gigabyte containers. And so with containers that large, it means that cold starts are very slow. And as we were dealing with this issue, we noticed that most modern autoscalers, both in Kubernetes and in Ray at the time, suffered a lot of thrashing. And so this was interesting as a challenge for the control plane because the control plane was responsive, right? Many of these use, say, bang-bang controllers or other simple control loops. And the challenge is when you have long boot times, which is a problem that's specifically relevant to large video models at high parameters, this leads to a lot of resource idling. But the second challenge was particularly more pernicious. And so this was a lot more challenging, I think, to debug as we began to scale. And this was data plane fault tolerance. And so what I mean here is this is referring to our GPU fleet that's actually executing the video generation. First and foremost, one of the first challenges we hit is video models are quite heterogeneous. They're not simple like large language models with autoregressive transformers. They rather have many disparate separate parts. So you might have autoencoders, the actual diffusion model. You might have different text encoders. You might have post-processing and video encoding, which is CPU work. And so heterogeneous scheduling was quite challenging to operationalize across the fleet. That one was relatively simple to scale. That one was relatively simple to solve because we just moved to heterogeneous resource pools with varying generations of GPUs. But at scale, one thing we noticed as we began to cross into hundreds and beyond of numbers of GPUs is we saw very high hardware failure rates in the public cloud. And this is true across multiple providers, including Google Cloud or AWS, most of the large hyperscalers. GPUs inherently are just fault prone. And at this rate of 2 to 5%, we would see slow GPUs that would manifest as stragglers in scheduling. And we would also see sometimes they would have silent corruptions. Particularly pernicious is certain workflow schedulers, for example, like Knative and others, will end up routing more and more traffic to failing nodes if you don't have proper health checking. And that will actually lead to degraded quality of outputs. And in cases where there's silent failures or bit corruptions, this leads to a degraded user experience. And it's something that's actually quite difficult to notice at scale. Another thing that was pretty subtle is we began to roll out spot serving across our entire fleet, so we could leverage very deep spot pools across a variety of different cloud providers and regions. But one of the challenges here is that you often face correlated preemptions across your spot fleets. So when spot capacity is low, it hits uniformly, and you'll see preemption rates spike across your entire fleet. And so you have to develop systems that can remain tolerant to a big burst of capacity coming offline if you are going to use spot computing. And so I think this manifests as like the tail at scale, represented again at large GPU serving fleets across our clusters. And the last problem that I think was one of the hardest actually to deal with operationally for a small team like ours is that we have a geo-distributed user base. Like I talked about, video is universal. Anybody can create video. Anybody can consume video, even if they're not interacting with the models in English. And we do train our models to be multilingual, but this is something we faced really quickly, sooner than a lot of large language models face. And one of the challenges is the latency can be really high. And so we noticed, for example, users in Indonesia on mobile devices would be unable to upload images and actually schedule jobs in a high user experience, in a good user experience, essentially, especially in face of preview streaming, for example, which was very latency sensitive. So we made a lot of key modifications to our serving stack to address these three challenges. And one of the first ones that I think was really useful for enduring load across a geo-distributed fleet was introduction of the GFE, or the Genmo front end. And so this is essentially a cross-border deployed service. We operate in 100 different points of presence where we have edge containers that run and actually intercept requests and then interface to our backend systems. And so the GFE offered us a very natural point of scheduling while reducing network latency considerably to our end users. And so as a first step, this allowed us to continue to get away with single regional or single zonal serving for quite a while still tolerating diverse network conditions across our user base. And so this has actually proven to be really useful to have a layer in front of our actual core serving stack to deploy firewalls and rate limiting and other additional features as we've continued to scale. One of the other things we did is we actually ended up building out a complete clean slate reimplementation of our serving stack with a predictive autoscaler. This has been hugely beneficial. As I mentioned, there's a really unique problem that we hit, which was long boot times meant that simple controllers like bang controllers or other auto-scheduling policies, for auto-scaling, were not able to cope with the delays in provisioning. And so what we're able to do is utilize predictive autoscaling with smarter control theoretic algorithms in order to better allocate and predictively autoscale resources as demand bursts happen. We found that there was some amount of predictability to the workload, and so we could actually get away with this and significantly reduce cold start performance and improve performance while cutting down on the tail of poor user experience. Really notably, one other thing we had to build, and this was particularly difficult, was health checking at scale. There's a million things that can go wrong, and this can again be memory corruptions, this can be CUDA errors, error XIDs manifesting, or often we would actually just see silent corruptions where videos just looked worse as you sampled on them. And so this was particularly challenging, and so we have rigorous health checks and burn-ins that run continuously during real user serving. So we can continuously probe our infrastructure and ensure it's serving results accurately and faithfully for what we need. What's also exciting is that in order to better deal with correlated spot preemption across our fleet, we now serve in 20+ data centers across the world, and this was kind of necessary for a product of our scale, given the GPU chip crisis. There were times I remember that we were consuming almost every single GPU that was available in various GCP regions. I mean, they were basically returning stock out in multiple different correlated, separate regions. And so at that point, the vision of elasticity was really more of an illusion. And so here we multiplex across reserved instance pools in on-prem or manage our dedicated data centers along with public clouds and work with cloud partners to provision long-term reservations for compute so we can always be ahead of our compute requirement needs. And so by balancing spot computing with reservations, we maintain a high degree of elasticity for that peak to trough autoscaling while significantly reducing aggregate cost and ensuring we're not paying on-demand or rack rate prices. One thing I'm very proud about is our latest training supercomputer. And I talked a lot about our inferencing stack, but we recently set up ICE, which is one of our newest training supercomputers. And so in aggregate scale, if you ranked in the top 500, it would be in the top 50 at least. And it's 98% powered by carbon-free energy as it's located in Iceland. And so Iceland roughly has a 70% hydroelectric and 30% geothermal energy mixture. And so I think this is actually really interesting because AI doesn't have to boil the oceans. It is possible to achieve massive scale and continue to provision these large data centers while still being able to remain green and friendly to the climate. So what's next? Video presents a series of extremely challenging problems for foundation models. I actually believe video will be one of the hardest foundation models like we as a community have ever trained. And I've talked about serving challenges. I think that's particularly hard, and that's just one of many aspects of our entire end-to-end ML system stack that we've rebuilt inside of Genmo to endure this scale. But at a first order, data is hugely challenging. We already operate at the multi-petabyte scale, and so that's extremely resource intensive, and it's very hard to actually operate when some of our training jobs need order a terabyte plus per second of storage I/O. Moreover, compute infrastructure is also extremely challenging. I mean, if you look at this, I think they're roughly 100 times more expensive at minimum to serve than image models like Stable Diffusion. And so I remember when I was in student research at Google, the Imagine Video project that was trained in 2022 or so, I believe, the team ran out of compute quota multiple times and just maxed the amount of compute that Google, which seemingly has infinite compute internally, was willing to allocate. And so video models are really challenging, and so that's fundamentally an ML systems scaling problem. Third is models. What's really interesting is there's no set playbook for how you should train video models. For LLMs, I think there's no secret now. The best training recipe is pretty much public knowledge. Like, I think anybody with enough resources and talent could actually replicate state-of-the-art AI performance now because the architecture is known, the data mixture is known. All of these details are known within the community. But for video models, it's a complete greenfield. And that means architecture and systems have to be completely redesigned. For example, one challenge uniquely with models is hardware systems and architecture co-design to enable long context training, for example. We've put a lot of resources into this, and it's a completely new area. There's very little academic literature in this space. And lastly is safety. I think safety is incredibly important for models as they continue to scale. And video brings in entirely new challenges for safety. I think it's really important that foundation model trainers work to ship their models to production and get them in the hands of real people. By getting in the hands of real people, you actually learn what the attacks and defenses need to be for these systems while we're early. I think across the field of video generation, nobody's going to say that this content is production worthy or really high-end or indistinguishable yet from reality. And so we are early, and that means it's actually net safer to ship real systems to real users and learn what the attacks and defenses are before this tech gets better. And so I think that this is an incredibly interesting future area of exploration too. And so our goal is to build the world's best world simulators. And these are engines that can simulate anything, impossible or possible. Today I've talked about creative applications for this technology, but I think long-term video generation will have a lot of impact to revolutionize areas, even including AR, VR, or embodied AI. I actually spent a bunch of time in self-driving. My first company I worked at was acquired by Tesla, and it's interesting because that space is entirely data bottlenecked. And so if we had really powerful video generation models, I think the self-driving problem would become trivial. So it's like, if we think about this in scale, there is where we are today. But over the next decade, I think video will come to be one of the most important modalities for generative AI as a whole. We're scaling the team really quickly. Today, we are at less than 15 people, and we've built this whole stack end-to-end and re-engineered the full stack and really are tackling really meaty systems problems. But if you're excited about the boundary of ML systems, please come join us and send me an email at pj@genmo.ai. And I would love to take any questions now. Thank you. Hi, please use the microphone. Thank you.
So one of the questions I'm curious, I'm still learning about space, so maybe basic. So a lot of models to video models, right? Sometimes the quality is good, sometimes bad. I tried pretty much all the major ones in market. So curious, how do you guys deal with controllability to control the product quality?
Yeah, just to repeat the question. So the question was, for video models, how do you approach controllability and steerability at scale? Is that correct? Yeah. So I think controllability is a really interesting emerging problem. Today the interface is text, it's prompt. And I think it's really interesting because pretty much anybody can access the product across the world, and they kind of have the affordance from ChatGPT that they type text in and they get video. But I don't think this is actually the optimal interface. I think over time, you want character controllability. You want to control their dialogue. You want to control character motion. These are all really important parameters. It's very early though, and so I think today the state of the art in the field has just been prompt because it's kind of like what people are used to with ChatGPT today.
Do you use diffusion models in your product?
Yes, we use diffusion models. So actually, my co-founder at Jay was one of the co-inventors of one of the foundational diffusion architectures for the DDPM paper. So we're big believers in large diffusion models, but to be clear, he also invented text to 3D as a field. And so, people ask me, is it going to be straight video? Is it going to be 3D, guided diffusion? We kind of sit in the middle, I would say, roughly, between these two paradigms.
So do you believe that diffusion models are the future of text-to-video models, right?
So I think evidence seems to indicate that diffusion models are roughly something like an order of magnitude more sample efficient than autoregressive models for generation tasks. And so 10x is a lot. From systems, it's almost impossible sometimes to squeeze out an order of magnitude efficiency. And so in light of that, I do feel very confident that diffusion is going to be one of the most competitive approaches just due to its efficiency today.
Thank you.
Yeah, I have What's the generation, the pipeline latency like currently, I just tried it, on your website. It takes a couple seconds. What's the best latency you can get? Is it close to the real time right now, or is it still like 5 to 10 seconds for 30 seconds of video? Can you elaborate a bit more?
So today, just due to the sheer computational intensity of these models, for us, generating a 5-second clip takes about a minute, right? And we could throw more hardware at this. We could throw parallelism and do distributed inference, but that would be cost inefficient, so we choose not to do that. One of the things we did do is we built out a large edge network presence. So I talked about the Genmo front end. In there, we have actually distributed memory across our fleet, across the world, right, in 100 points of presence. And that serves as an essentially on-demand CDN for us to do streaming. And so that's what enables you to get that very short time to first pixel. But that was a trick we used in order to essentially balance latency and throughput trade-offs. But I think the question here about real time is really interesting. So, I think the way this technology generally goes, I feel, is make it work, and that's the stage we're in, make it better, and then you make it faster. And the trick to make it faster usually trades off quality. Like with GPT versus GPT, like 4 versus 4.0 versus 4.0 mini, they use distillation to do this and other tricks. And so there is a quality speed trade-off. And so I think because we're so early, we've chosen just to optimize for quality as much as possible. But I certainly do believe it will be possible. It just might be very expensive.
Thank you. That's a wonderful presentation. So my question is, for GPUs, are you trying to use heterogeneous GPUs, like whatever you have got, or are you trying to stick to a specific type, like, for example, L40s?
Oh, yes. We use heterogeneous resource pools because there's multiple models that we're actually serving in this entire pipeline. So it's not just a single big model like with an LLM, which is considerably simpler, I think, to orchestrate and scale and serve because they use homogeneous resources. And so you mentioned like L4s or T4s, or there's like L40Ss, which are particularly efficient. Like different components can use different GPUs. Like the core, usually the most expensive part is the core diffusion model, and that's going to be served on like large-scale data center grade hardware.
How do you manage this kind of coordinated approach if, for example, one IDC only have specific type of GPUs?
Yeah, so you can use it as fallbacks. I think that's a pretty effective approach here. So it just might be like less efficient or less cost efficient, but like flexibility is like really important as you approach scale, right? And so as much as you can build flexibility into your systems via failovers or points of redundancy, like it's really important so that you can cut that tail, this like kind of tail, the poor user experience at the tail here, right? And so that's an example of a particular type of problem that's actually fairly common, right? Like you may get stockouts in one GPU class, but that may not be the case in another. Yeah.
Another thing you mentioned is you're trying to avoid on-demand costs. But how are you going to deal with the surge? You're just showing the image.
Yeah. No, it's really interesting. I mean, certainly it's not always avoidable, right? But one thing that we've been lucky with is as we've just grown, this peak to trough auto scaling has become more muted, right? Like as our product has propagated more globally, users begin to fill in the valleys, which is kind of interesting. So there is like auto scaling, but we're starting to see that stabilize, and I think that's just like driven by further globalization of our product. If you're an inference provider or you have like a very US-centric audience, like I assume that's like something you're not going to have the luxury of doing, and so it's harder to kind of have more predictability in serving. But that's something that we're lucky, like with a global user base, they actually kind of demand fill in quite neatly.
Couple of questions. The first one is there's a lot of high-profile team there are investing in text video, like OpenAI Sora, like Pika, right? They all like have amazing talent there. Just curious how you guys train your data or train your model, build it differently, and that can give you guys a competitive advantage. The first question. And second question, hope it's okay, ask one more. So I found a lot of models. So some models, they are use case wise. It might be better in certain type of scenarios because they train a lot of data in a certain type of scenario. So just curious, is certain use cases your team are very strong at, excel at? Thank you.
I'm sorry, could you repeat the second question? Sorry.
Oh, the second question about use case wise, right? Just text to video generation, like sometimes there's so many models out there. Some are better at certain situations. For example, someone eating food, someone changing clothes. So those kind of data, because they train a lot, so better. Just curious for your team, like specific user cases you guys really good at, or you trying to focus, right? It's really hard to be good for generic all type of use cases scenarios. Thank you.
Yeah. So I think the most important thing when I look at video is motion. I think like the only uninteresting video truly is one that doesn't move, right? And so in that case, motion is the most important thing. And so I think it's really interesting. We view these models as world simulators. And so it's really interesting, how does inertia manifest in the model? Is Newton's third law reflected? Is optics and viscosity reflected effectively in the model? Like, these are fundamental properties of the world that you can measure and you can actually test in the model from a capability standpoint. I believe like our model is one of the better ones from a motion standpoint, right? And I think it has good fluidity of motion, realistic motion. I think this is fundamentally really important. As a broader point, I think we're so early. We're 1% of the way there to our generative video future. Like, for me, it's like, when can it be that like a kid anywhere can take their phone out, push a button, and get an Academy Award level winning film? And like, I think we're years away from that. We are so far from that happening, and there's so many little sub problems there. And so I think a lot about this is just it's pure technology right now, and developing the best infrastructure and models ultimately co-optimize to produce the best technology and the best models, and ultimately the best motion. I think that's most important.
Thanks, very nice talk. I have a question, a bit open. Have you considered having a more scientific approach for the type of models or inference you have? I mean, from what you said, you have a background that is more research-like. So what about trying to find patterns from these video outputs that we have? Is that on your radar?
What's interesting about video models, like especially in the case where they're world simulators, is it's kind of like rising tide floats all boats. Like, improved ability to simulate some fundamental property of the world just makes all videos look more realistic, whether you can tangibly point to it or not. And so, you know, we've tried like optimizing for specific capabilities. Like, if we were strictly purely like product focused, I think that would be the right approach. And there's many other companies that are purely product focused companies in the space that do this. But I think that's not the best way to produce the best fundamental foundational technology. And we definitely see, like, for example, one thing is we were one of the first models in the market to make a model that could do walking, like human walking. Normally, it's really interesting. Like, older models used to just like make people who would hover, like they didn't move their legs, right? And that's a really deep thing that the model has to learn to understand. And so you could fine tune for that capability specifically, but we found really interestingly that just emerged with scale, right? With more data, more parameters, more compute, the model learned to walk, right? And so that was ultimately the better place to invest our innovation tokens ultimately, was in the just base scaling, base capabilities, kind of world reasoning above just like specific point use cases.
I think that's all the time we have. Thank you for that wonderful exchange, Paras. Thank you.